Hello, this is the fourth video in this lecture, and this video will review the confidence intervals very briefly. And confidence interval is a way of estimation, and in the second part of the review, we learned that the sample average is the best estimator for the true average, true mean. However, so you may view that as a point estimator because there is an unknown mean, and you are estimating this mean by simply one number. So when you use one number, it cannot be correct, right? Almost always you are going to miss the true value, even if your estimator is accurate and could be close enough to the true value, but it will never be true. Probability is virtually zero. So then, and also another problem is when you just say that, so what is the average, the expected income or expected return from the stock market in 2021? Then say my estimator is say 5% point. 5%. Even if it is a good estimator, it does not tell you how accurate that is. So 5%, say 5% is correct estimator. But if I'm doing a very good job, then the potential error will be very small. But otherwise, if I'm not doing well or if I don't have enough data, then the potential error will be much larger. So like say, when I say 5%, it may include plus minus 10% error, or if it's very accurate, it may include a potential error of plus minus 0.1% point. So in those two different cases, your investment strategy will be different. So point estimator, 1 point is not enough, does not deliver enough information in many practical situations. Similarly, like for example, when you look at like say presidential election predictions, in those predictions, in small prints there are margin of errors, or you hear that say this candidate is leading the election out within the margin of error, or the lead is greater than the margin of error. So the margin of error is another very important information in many estimations. So confidence interval is doing that. Confidence interval incorporates the margin of error within the interval. So the idea is there is a point estimator. Okay, this is good, but let me tell you what is the margin of error. So then you put a certain margin of error around the point estimator, then you will make an interval from the estimation problem. So, and on top of this interval, I also tell you that what is the percentage of this interval to be true. So like for example, when I say 95% confidence interval for the true population mean, it says I will give you an interval which is likely to contain the true value with 95%. That is the idea of confidence interval estimation. And by the way, here is a small digression. What is random here? Conceptually, it's a very conceptual question. The true value, I said, the true population mean is not random. So this probability, the probability cannot be from the true parameter. So the idea is the true parameter is here, always here, but your data may be different. So when you have the first set of sample, then your estimator will be like this. And from if you resample the data, then you may get something like here. And so if you resample again and again, which is purely hypothetical, but if you can do that, then your interval will be moving around the true parameter. So then after all, 95% of the cases will include the true parameter. That's the concept of this 95% probability. And mathematics, it's complicated, but again, the idea is simple. We know that the point here is this is the data and this is unknown population mean. So the difference is the estimation error. So when you estimate the population mean, the best estimator is the sample average. And still there are random errors, estimation errors, which is this guy. There are differences. And you standardize the estimation error using the standard deviation, right? And then this captures the standardized estimation error. And we know that this standardized estimation error follows a standard normal distribution. So this distribution is known. We know how it looks like, how likely the error is. So then, and previously after some tedious algebra, you can show that if you choose 1.96 plus minus 1.96, then between plus minus 1.96, the standard normal distribution will have 95% probability. So going back here, where is it? So the probability on the white area will be 95% if these thresholds, both endpoints, are plus minus 1.96. So using this property of standard normal distribution, you may deduce that those two intervals will have the true parameter with 95%. So, or if you just look at this final formula, what it means is that first, y bar does not change. That is the center of the interval, which is the point estimator, because the sample mean is the best estimator for the population mean. You choose the center of the interval using the point estimator y bar. And what you want to do here is you are going to allow certain margin of error around the point estimator. The margin of error is 1.96 times standard deviation divided by square root n. So standard S over square root n is the standard error of your estimator. So standard error is a measure of your estimation accuracy. So use that and multiply a certain constant, which is 1.96, again from here. So and in practice, many people just think it as y bar plus minus 2 standard errors. So 1.96 is approximately 2, and this is the standard error, which is usually calculated by the program. So the mean is also calculated by the program. So rule of thumb is the mean sample average plus minus 2 standard errors. That's what practitioners usually simply say, and not that wrong, but I want you to understand the basic flow of the theoretical background behind it. Also, then the point here is it also relies on the standard normal distribution assumption, or the central limit theory result, the standard normal distribution approximation. So the sample size must be large enough, and we also use the idea that the sample variance is correctly estimating the population variance. So and it's also intuitive. There is nothing surprising. There is no surprising result. Instead, all the results are so simple, so intuitive. So that's rather a surprise. Without knowing the mathematical background, you can understand it, I believe. So that's rather surprising how powerful, how useful, and how simple the results are. And then finally, this is the final summary. Then what we are going to assume later is that the sample observations are randomly sampled, and some mathematical assumption that the expected value of fourth order is finite and strictly greater than 0. It's not a big deal. I'm going to ignore this assumption. So then the random sampling is the only problem. Otherwise, and additionally, large sample size. I have not mentioned that. So that should be stated as number 3. Large sample size and random sampling are two pillars, two foundations of our theory. That's all. So that's fine. And then in the next lecture, we are going to start the regression analysis. We will start regression models, and we are going to use the motivating example again. So our motivating example was the effect of student-teacher ratio on test scores for elementary school students, like 5th grade. So, and we actually have real data, and we already have scatter plot. I will use this example to introduce the regression model. And so this chapter, the review chapter, was a review. So I skipped a lot of things, and I went through very quickly. But from the next chapter, I will be more careful. I will spend more time on each of the important topics. So, okay, thank you for watching the video, and I hope you recall what you learned in a statistics course, and we'll see you in the next lecture.